So let's go over what happened last time. This is a very, very important idea that will be very difficult, I think, right? So we need to figure out how to deal with overcounting. And here is a very, very simple case of where that might happen, right? So you have two white pawns and one black pawn. The white pawns are indistinguishable among themselves, and the black pawns are indistinguishable among themselves. And you want to know how many linear patterns are possible. So this is one linear pattern: white, white, black. Yes? So because there are very few cases, you can actually go through all the patterns systematically and see that the possibilities are exactly three: white, white, black, or white, black, white, so black is in the middle, or black is the first. So there are only three possibilities. But once the number of items becomes larger, doing it directly becomes very difficult. So what you should try to figure out is what I call the Kafka document. If you read Kafka, the Castle, right, it speaks about bureaucracy, an insane, surreal bureaucracy. And so what we are doing here, we are becoming very efficient bureaucrats. Okay, so similarly with students, again, I tend to not remember names very well unless the names mean something significant. So I imagine that the pawns have each swallowed a unique positive integer, and this way they are now all distinct. It's swallowed because I cannot see it, so I cannot tell really when I look at it. I do not know if I'm seeing 2, 1, and then 3, or am I saying 1, 2, 3. But in this case, I imagine that they're all visible to me. If I know them, then I can produce the Kafka document where I have 3 inputs. You see this? 1, 2, 3, where I list pawn number 1, pawn number 2, pawn number 3, and I list all of them. If you remember the previous lecture, there are 3 factorial such documents possible, each corresponding to unique linear arrangement. So far, everything's clear? Okay. So some of those documents are redundant. They describe the same situation because I cannot tell whether pawn 1 or pawn 2 are where they are. I can only tell patterns like white, white, black, right? So what we have here is that we have 2 documents from this file that correspond to white, white, black. Good. And for every other pattern, I also have exactly 2 documents corresponding to it. Do you see why? So for example, if black is in the middle, that means 3 is in the middle. And then the bounding pawns can be either 1 and 2 or 2 and 1. So 1, 3, 2 or 2, 3, 1 is a code for the same recognizable pattern. Okay. And similarly, the last file represents black, white, white. So you see what happened here. Now, no longer does the document stand for the unique situation, the unique pattern, but rather the pile of documents. The whole heap of documents stands for the unique situation. In other words, each actual thing that I can observe has exactly 2 words. In this case, WBW has 2 words that describe it: 1, 3, 2 or 2, 3, 1. You follow me, guys? Shake your head like this. You follow me, that you understand, right?
Yes. Yeah.
Great, great. That's excellent, guys. You have to keep it in mind. Okay, keep in mind. So now I realize not the codes, but rather the piles are counting unique situations. So each pile is a different situation, and I need to know how many piles I have. So in this case, I know I have altogether 3 factorial documents, right? And each document has a synonym. In other words, 2 documents per pile. So I take 3 factorial, divide by 2, and I get the number of piles. Understand? That's what I try to say here. The number of piles times the number per pile equal to the number of documents. That's the idea. So I was able to create codes for the documents, but there is a redundance because the number per pile is not 1. So there is a redundance. So I can figure out the number of piles by writing number of documents divided by number per pile. Again, that only works if each pile has the same number of documents. Otherwise, this technique is not useful. You understand? So like in here, we have 2, 2, and 2. Good. So then we know that the number of piles correspond to the number of unique solutions, and this is how it's obtained. So here is an example, first example, we already covered it, where it's not convenient to go and directly list all the possibilities. So here we have a bunch of pawns that have the same color cannot be distinguished, and we have 6 pawns, right? So we can construct, using that idea before, we can construct a Kafka form. And the Kafka form, again, imagines that each pawn has in its belly a unique number. So also the numbers 1, 2, 3, 4, 5, 6. They're supposed to be in the belly. Why in the belly? Because I don't see them outside, so I cannot distinguish them, right? So when I see white, white, it might be 1, 2 or 2, 1. Okay. So if I imagine that all of them are distinguishable, there are exactly 6 factorial ways to fill out the form. So for instance, that is one way to fill out the form. 1, 2, 3, 4, 5, 6. That will correspond to this pattern and have the specific arrangement, right? But I can interchange 1 and 2, and that will still correspond to the same pattern arrangement. So far you understand how I calculate 6 factorial? That's because, again, we have the generalized principle of counting. 6 possibilities here times 5 possibilities here times 4 here and onwards, right? So that's why it's 6 factorial. You don't ever have to memorize when you multiply, you just understand. Okay, so then this corresponds, this code, it's one word that will describe the pattern WWBRRR. Okay, but there are other patterns, other codes that will describe the same pattern. So there are a bunch of redundancies in my code. Now, how many redundancies per pattern are there? So how many redundancies are there for this pattern? So first I'll do it intuitively, and then I'll do it in a way that might confuse you at first, but it's a very good way to train yourself to think like a bureaucrat. You understand? If you are able to think like a bureaucrat, you will avoid 70 to 80% of the mistakes that people in probability make, maybe even more than that, okay? So first, intuitively look at it. I can see I have 2 factorial rearrangements. Here I can only rearrange it once, and here I have 3 factorial possible rearrangements. So it's 2 factorial times 1 factorial times 3 factorial. If you don't believe me that's true, I will explain below how I know that more precisely. And the more precisely actually might confuse you, okay? So it will be 2 factorial times 1 factorial times 3 factorial. And notice that if I take any other color pattern, it will also have 2 factorial times 1 factorial times 3 factorial rearrangements, which means that each color pattern has exactly this many 2 factorial times 3 factorial synonyms describing it, right? So this corresponds to what? In terms of my paper analogy, this number is what regarding my documents? Could anybody tell me? Yeah, go ahead, Sean.
Is it the number per pile?
It's the number of documents per pile or the number of synonyms that a given concept has, right? So for example, I don't know, Eskimos have maybe 13 words that describe snow, right? So snow, you imagine the actual object snow or snowflake or whatever it is, and then the words that describe it. So in our case, words are those numbers, right? 1, 2, 3, 4, 5, 6 is a word. It describes this actual object, right? So the object is not a single pawn. The object is all the things that we're observing all together. That's my object, okay? Like a chain, if you want to imagine, like a bracelet, linear bracelet. So white, white, black, red, red, red. This corresponds to a word that describes this pattern, but there are many other words. They're exactly 2 factorial, 1 factorial, 3 factorial, such words, okay? And so all I have to do is I have to count how many piles I have, right? So 1 pile corresponds to 1 pattern. How many piles do I have? Well, I take 6 factorial and I divide by this number. So 6 factorial is the total number of documents divided by the number of documents per pile gives me the number of piles. You follow? Say or write yes if you follow, or write no if you do not, guys. And yeah, good. Follow, yes? Thank you. Wonderful, guys. So never hesitate to stop me, right? And never hesitate to ask questions. It's a very, very tricky subject. If you think others understand and you are not, most likely you have to, your self-esteem is a little too low. Most people don't understand it well at all. Okay. So I'm going to now give you a more elaborate explanation of why that is the case. Why is it 2 factorial, 1 factorial, 3 factorial? Okay. So what I'm going to do now, I'm going to devise another document. So for that other document, let me imagine two things, right? So let's imagine that we have all the numbers by themselves. So each pawn has a number, and each pawn also has its color number. So for example, there is a white pawn labeled 1 and a white pawn labeled 2, but we also label the white pawn as 1 white and 2 white, right? I colored it green here. The black pawn, it's labeled its general ranking is 3, but it has another number which is 1. Yes, and the red ones, that's red 1, red 2, and red 3. You understand? So I have this. So now suppose that for any pattern, right? For any particular pattern that I observe. So for in this case, it's white, white, black, red, red, red. But you can observe any other pattern. So I have a form, and on the form below I print white, white, black, red, 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 and then the form that I'm presenting, Kafka form, is as follows. So I have for white, I want to know in what order, in what linear order, what's the first white I see, what's the second white I see. What's, in this case, black is only 1, so what's the first time I see a black? What's the first time I see red? What's the first time I see, the second time I see red, and third time when I see red, for this particular pattern, you see? So let me, for instance, explain what it means if I fill in this form like this. If I filled the form as 2 1 1 3 1 2, if I put this code and the form is labeled like this, then I can quickly figure out where the white pawns were, where the black pawns were, and where the red pawns were. Do you see that? So what did it mean? 2 1 means that that I see, the first time I see a white pawn, the first white pawn moving from left to right is 2, then followed by 1. Doesn't matter where, actually, right? In this case, I know they're consecutive, but for any other labeling, it will be the same. Okay. So I can take this code and I can construct exactly where those pawns were in the pattern, right? So how many ways are there to fill out this form? There are 2 factorial times 1 factorial times 3 factorial ways to fill out this form. Okay, this is just to show you that if this is the pattern I observe, right? Given that I observe white, white, black, red, 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 given that I observe this pattern, all I now need to know is where are the respective positions of the whites among themselves, the blacks among themselves, and the reds among themselves. So if I fill this form, independently this can be filled, this box is filled, and independently those 3 boxes are filled. That's why we have 2 factorial times 1 factorial times 3 factorial. Each box represents an experiment that has a number of possibilities. This experiment has 2 factorial possibilities. This experiment has 3 factorial possibilities. This has only 1. Do you follow me? If you do, write yes. I'm trying to explain why I have this. I mean, I did it intuitively here, but I want you to understand that you want to think very procedurally, like this document. Now, if I label this document anywhere else by any other letters, right, any other arrangements of whites and blacks, and I can fill this code, I will be able to figure out what is the pattern. Knowing this labeling, and this will just measure where they are relative to themselves. Okay, so for example, maybe the form is labeled WRRWBR, which means I first see a white pawn, and then I see a red pawn, then I see a red pawn, then I see a white pawn, then I see a black pawn, then I see a red pawn again. You understand? That might be another form. The form would look the same, but would have the different labeling. Instead of this label, it would have this label. You follow me? So then, if I put in this code, for example, the code 211312, putting in this form will correspond to the absolute pattern code which is written here. Understand? Because this means that when I look, first white pawn I see is the second pawn. Then as I move on, the fourth pawn that I see is white pawn number 1, right? Then the first red pawn, which is the second position here, will be black. So the first red pawn would be 3. So it would be, in other words, you see, first I see this white numbered 2, and then I see a red. The red here will be 3. Labeled 3. Then I see another red, which will be labeled as 1. Then I see a white labeled as 1. And then I see black labeled by 1. Then I see the final red labeled as 2. Okay. and the absolute pattern is 264135, which is I obtain it from reading below here. Understand? The point is again to show that indeed each particular pattern can correspond to the same form, and by this form I know I have 2 factorial times 1 factorial times 3 factorial synonyms or documents in the pile. I hope you understood this more elaborate explanation as well. Okay. So altogether, I now know that 6 factorial is the total number of documents divided by the number of documents per pile. And that gives me the number of piles, and by that I know exactly how many distinct linear patterns that I can tell apart, that I can produce. Here is another example. So how many arrangements or rearrangements of the word necessary are there? You see, necessary. Go ahead and try to solve it, guys, and type in the comments what's your solution. Shabeli, is your bunny with you or not?
He is. Oh, under the bed.
Professor?
Yeah, go ahead.
Do we put the answers in the chat, or do we like?
Yeah, best put it in the chat, and I will see what it is. Yeah. You don't need you don't need the calculations, just the form of them, right? I mean, you can press the calculations in the machine. Okay. I think a bunch of you are ready, and I'm glad about it. Let me know if you would like to continue. All right, so a bunch of you, see if everybody, maybe some people are still working. All right, ready? So here is the situation, right? So I imagine that each letter, it's now the same as pawn. Each letter is the same as a pawn. And in general, I cannot tell n's apart or e's apart or c's apart or s's apart, right? They are all the same. But I imagine that somewhere on there, maybe they have a serial number. So the first, so we have how many copies of N's? We have one copy of N, we have two copies of E, we have one copy of C, two copies of S, one copy of A, one copy of R, one copy of Y. Good? And so you can reason if you ever forget, always try to reason as we did before, but now it's the same situation as with the points. We have altogether 9 letters, so 9 factorial documents divided by 1 factorial. Those are how many rearrangements of N, 2 factorial rearrangements of E, 1 factorial rearrangement of C, 2 factorial rearrangements of S, 1 factorial rearrangement of A, and 1 factorial rearrangement of R, and the same for Y, which are kind of, it's annoying to write them, so it's 9 factorial divided by 2 factorial, 2 factorial. Good? Guys, so not only is it, so if you just got it, that's great, but be very, very worried that you know very absolutely cold how you were able to do that. Okay, here is the next question, also hopefully simple. We have 10 competitors. We have 4 of them are Russian, 3 of them US, 2 British, and 1 Brazilian. And once they are ranked based on their performance, they are not ranked by name, they are ranked only by country of origin. How many distinct patterns might we observe?
Was this get? For the viewer, the venues, you have no clue.
Yeah, you are breaking a little. Could you maybe, I'm not sure if the connection is, I don't understand what you're saying. Interpret, apologies for mispronouncing your name. Accident, okay. All right, so let's look through it, okay, guys? So you all imagine exactly what outcomes are listed as, right? So for example, maybe the outcome listed on the board would be R, U, U, R, B, U, R, R, B, R, B, R. Yeah? Okay, so you see that's also the way the outcomes are listed. So we can imagine that we list all the individuals separately. There are 10 individuals, so there are 10 factorial possibilities of listing them as individuals. But we have redundancies. We have 4 factorial redundancies for Russian, 3 factorial for US, 2 factorial for Britain, and 1 factorial for Brazilian. And I hope you guys that I'm not going through the entire conceptual process here, but I hope you are, at least until it's completely obvious for you. Okay, this is the general situation. In general, if you have n objects that are to be arranged and 1 of them are not distinguishable among themselves and 2 are not distinguishable among themselves, so maybe n1 means white pawns, and 2 means black pawns, and 3 might mean red pawns, and so on, right? So there are k categories, and within each category, items are not distinguishable. And over the categories, of course, we have altogether n items. The total number of ordering is n factorial over n1 factorial and 2 factorial all the way to n sub k factorial, okay? So that's overcounting. That's extremely important. I think that you understand it. It will be very complicated later. Understand it in this form in terms of the documents and why you multiply and why what we wrote here is completely obvious. Okay, so let's move on to the next lecture. So now we are going to talk about combinations. So combinations, this is the problem, right? So imagine, imagine that we have n objects. Maybe those objects are distinct students, and we want to pick a subset of size r. Maybe r of those students will join the class, or r of those students out of n will go to a field trip. Okay, and yes, and where was I? And so we can imagine that the selection is done as follows, right? So we need to figure out how many selections of size r are there from a set of size n. Make sense? So let's say if I have 10 students, how many subsets of size 5 students can I have them? So here is how we can perform this procedure. We can imagine that all the objects are going to be arranged linearly, and then below those objects there are two trays. One is the red tray, and that is the red tray contains r places, r placeholders. Everybody who is on the red tray will be selected, and everybody not on the red tray will be on the blue tray, and they are not selected. You understand? So I have those those n objects, and I perform the selection this particular way. So by any chance, guys, you see, so the objects are all distinct. So you do see the numbers on top of them. If those are students, you see student 1, the student is holding a sign that says 1, another holds a sign that says 2, 3, etc. Right? So this is just a particular arrangement. Okay. How many ways are there to select those students? Okay, so clearly there are n factorial orderings of those objects linearly. So this is one particular ordering, but how many rearrangements are possible? You see, once you place a particular sequence, the objects in the red tray can be permuted among themselves. So there are going to be r factorial permutations of those objects among themselves, and n minus r permutations of the objects in the blue tray among themselves, for a total of r factorial times n minus 1 factorial permutations. Do you understand? So what I'm saying is it's a similar procedure. I need to construct documents, and how do I decide how many of those n factorials are selected or not selected? So given a particular code, I just truncate and put the first r of them as selected, and the next n minus 1 is not selected. And then I see that I can rearrange. I have another form, just like we had with the previous explanation. Altogether, we have r factorial n minus 1 factorial ways of rearranging, for example, this particular grouping, you see? So I can take 1 and change it with 2, 3 and change it with r. No matter how they are permuted here, nothing is changed. The same people are selected. No matter how the others are permuted among themselves, nothing is changed. So since there are n minus r objects here, it's n minus r factorial, and this is r factorial. So now all that remains to be done is this is n choose r. Just take n factorial objects and divide by r factorial, n minus r factorial. Good. And what we say is that n choose 0 is equal to 1. Clearly, that's by definition, because there is only one way to choose nobody from the set, right? So you choose empty set, and there is a 1 set. And to make this true, to make the formula still work. So this is n factorial divided by 0 factorial, n minus 0 factorial. So this is just n factorial and n factorial. They cross out, and we have 1 over 0 factorial. That has to equal 1. So we define 0 factorial to equal 1 as well. And here is your first question. 3 students are selected from a group of 4 students to go on a field trip to Greenwood. How many choices are possible? So this I selected to have very few possibilities so you can actually see it and then calculate it. Yes, so very good. You can simplify it completely or look through the possibilities. Okay, guys, and anybody here, if you are confused, the slightest confusion, you tell me. We can go over that. Okay, so here is that situation with the students. So you now see their numbers displayed. So student 1, 2, 3, 4. Okay. And green here means not selected, red means selected. Okay. What is the Kafka document that describes this situation? So my Kafka document would look like this. It would have a bar, and the bar here does not have dividers. No, me got kicked, but I think I'm letting a person back in. I'm not sure what's happening. I'm admitting it, just not joining for some reason. See, guys, so somebody for some reason got kicked out, and I'm not able. I don't know what's happening there. It just says joining. I don't know. Well, we'll deal with it maybe later. I have no idea what I can do here. Okay. Okay, guys. So you follow the document. I envision is the following, right? So I imagine one bar containing 3 numbers. There are no dividers between those numbers, and those numbers are the individuals that were selected, and they have to be listed in order. Okay. So for example, this means 1, 3, 4 individuals 1, 3, 4 were selected, and 2 was not selected. Okay, so I can fill this document this way, but I can never write 1, 4, 3. Okay, you see this? So this is not allowed in my document, and then I can just simply count the number of documents that are possible. Clearly, maybe 4 is kicked out, that's document 1, or 3 is kicked out, that's document 2, 2 is kicked out, that's document 3, and 1 is kicked out, that's document 4. So you can do it directly. You don't have to write the papers actually, but you just can imagine them. There are exactly 4 possibilities. And this is confirmed if you just do 4, choose 3. It's going to be 4 factorial over 3 factorial divided by 1 factorial. 4 factorial can be written as 4 times 3 factorial. So we cancel the 3 factorial and we get 4. Yes? Milika, you're good? Everybody's good? Excellent, guys. I just really worry if anybody doesn't understand something. Great. And you understand how I got the general formula?
Can you explain how you plug into the general formula again? Sorry.
Well, give me 1 second. Yes, apologies, guys. Just apparently some student, for some reason, hopefully not because of me, because I'm admitting the student, but the person is not able to log in. Okay. So yes, once again, somebody asked something. Could you repeat your question?
Yeah. Can you show me how to plug into the general formula again?
Yes. So in the general formula, you see, look at it, right? You have for this situation, you take the top number and you write the top number factorial divided by the bottom number factorial, and here you take top minus bottom factorial. So 4 minus 3 is 1 factorial. And you should kind of think about it, right? Why is that the case, right? So look at the situation. So what we have here is altogether there are 4 factorial permutations. You agree? 4 factorial ways to put them in a line. But once you put any permutation in a line, 3 of the elements in this line are in the red tray and 1 element is in the green tray. The green tray means not selected. Now, the elements that are within the red tray can be rearranged with one another. There are 3 factorial rearrangements. And the elements in the green tray can also be rearranged among themselves. So we have, in general, this is the situation, right? You would have n minus r. If we need to select r elements, then the selecting tray contains r placeholders. And the not selecting tray contains the remaining placeholders, n minus r, right? So for every given permutation, this is just the identity permutation, 1, 2, 3, they're all in order, right? 1, 2, 3, all the way to n. Now look at it, right? This means that first individuals 1 through r were picked and individuals r plus 1 through n were not selected. But if I take another permutation where the elements 1 through r stay in the red tray and the elements r plus 1 all the way to n stay in the blue tray, no matter what the permutation is, that corresponds to the same pattern, so of selected individuals and not selected individuals, right? So we know that how many permutations correspond to this pattern. Exactly r factorial times n minus r factorial. So those are the synonyms. Those are the documents in your file. Okay, so you take total permutations, divide by the number of synonyms where this is the selection pattern.
Okay.
I hope it's clear. It can be very complicated, especially at first, right? And once this is clear, you know that every permutation can be, every particular selection can always, you can list it in order. So if individuals 1, 3, and 4 were selected, I can enforce writing them in the form as 1, 3, 4. So you see this form, when I don't put the bars, that will now be combinations, and that will be very useful. Okay. And here is the next question, guys. So we have a group containing 5 women and 7 men, and we have to create a committee that will contain 2 women and 3 men. So first part is, how many possibilities are there? How many committees are there given this information? Out of 5 women, exactly 2 picked for the committee, and out of 7, 3 men picked for the committee. How many possibilities there? And the second part is the 2 men. There are 2 men that don't like each other and they will not be on the committee together. How many possibilities if that's the situation? Okay, go ahead and try to compute. Your goal, guys, is also still simple questions. Your goal is to compute them, but with procedure, right? So can you imagine a document, a Kafka document that guarantees that you don't make mistakes? Naomi, welcome back. I'm sorry for the trouble. I'm glad you were able to log in finally.
Yeah, I don't know. I think my computer was just having some problems.
Oh, yeah, great. At least it's not me. And once you answer it, guys, perhaps somebody would like to describe what sort of document have they constructed for this problem. I'll be right back.
Try explain number one.
Great. I would be very, very glad if you do. Just let's wait a tiny bit longer. I want to be sure that everybody actually was able to think about it. Very nice, by the way. I hear your voice, which amuses me because it's very not Russian accent. It's very strange. I would have not guessed you're Russian.
Trying.
No, try to be Russian. What is that? You should be proud. Russian and proud. When I was developing too much of a different accent, I started on purpose meeting A or you know what you call them, articles, so that they would know that I speak Russian.
Because what they think, if you're Russian, you're better in math or something.
No, people think I'm not sure what they think about Russian. Usually they think if you're Russian, you're dangerous, right?
Yeah, but what articles you saying? Academic articles you read?
No, they or a, right? So I say.
Oh, okay.
Yes. I am man, right? That's the type of thing that you say. Are you ready, guys? Shake your head like this if I can see your face, or say yes, ready. And yes. Great. And Milika, as you are doing this extraordinary effort of actually even through Zoom going through this class and the other, you follow so far, right? You're with us. Excellent. I'm so proud of you. You can't imagine how I'm happy. All right. Just okay. So Valeria, go ahead. Try to describe one.
So we have 5 women and 2 options for the seed. So 5 factorial choosing 5 factorial over 2 factorial.
And something else is missing. So you can say 5 choose 2, but the formula would be 5 factorial divided by 2 factorial and also 3 factorial on the bottom, because the numbers on the denominator have to add up to 5, 2 and 3.
Oh, okay.
Okay.
So 5 factorial over 2 factorial multiplied by 3 factorial?
On the bottom, yes. So numerator 5 factorial, denominator 2 factorial times 3 factorial.
Why there is 3 factorial?
Oh, great question. That's what I mean, guys. So you think about it again and again and again. Why is there a 3 factorial? You have to very carefully understand how we design this experiment. You understand? It's really from our decision. So I need to devise a counting mechanism that will tell me how many subsets of size R for any R are there from a set of size n, right? So we did it, for example, here I just selected a very, very trivial example because it's very easy to list all the possibilities, right? So 4, okay? So my idea is this, right? So I have, let's say, 10 individuals. Let's say we have 10 individuals and from them I'll select 3. We're good, guys? 10 individuals and 3 if you don't like those letters. So what am I going to do? Those individuals are each, they have a number on their neck, 1 through 10, okay? And then they will be placed against a wall. And on the wall, you have like a tray. You see, you have a red tray, which means selected, and you have the blue tray, which means not selected. You understand? So you arrange those individuals. If I said we're going to pick 3 out of 10, so this red tray will only contain 3 positions. And the blue tray of not selected will contain 7 positions, 10 minus 3. You understand? So in general, it's containing R positions, and the other tray contains N minus R positions. Okay? Now, there are going to be a bunch of, I have N factorial permutations, right? So arrangement, basically, who is standing first, who is standing second, who is standing third. There are N factorial, or in our case, 10 factorial positions, right? But a bunch of those positions, so I print a bunch of documents, that 10 factorial documents I print. You know, the documents I imagine, they are documents where you have this box, and the box is divided into 10 parts, right? 10 parts, those are the documents. Now, a bunch of those documents will correspond to the same situation of selected versus not selected. I'm going to I'm going to arrange those documents into selected piles that are identical, right? So they select the same individuals. So suppose that people 1 through 3 were selected, and the remaining people were not. So 1 through 3, I could have the permutation 1, 2, 3, and then in the blue tray, 4, 5, 6, all the way to 10, right? Or I can have 2, 1, 3, or 3, 2, 1, or a bunch of them. I can have 3 factorial arrangements in here. And for each arrangement in here, I can have another 7 factorial arrangements in here. Do you see that? So for each particular pattern, if I rearrange any of the individuals on the red tray without moving them outside of the red tray, they're going to be exactly R factorial rearrangements multiplied by independently rearranging the guys in the blue tray, which is N minus R, or in my example, 3 factorial possibilities for the red tray and 7 factorial for the other tray. So they are going to be each situation. And if you don't understand, guys, by all means, stay after class. I will explain. I will make more drawings of it, right? It's very, very important concept. So if you understood, just to gauge, if you understood why you carry this procedure, write yes in the comments. And if not, guys,
So numerator and denominator numbers should be equal, right?
So the denominator represents so here is my analogy. See, so I have a bunch of documents printed out, and then I arrange them into piles. Each pile is of the same height, the same number of documents in each pile. Okay, and the number of documents in this pile is just like with the pawns that I did before. It's going to be the same, no matter what. It's difficult to list, right? So here I have R objects. And here I have N minus R objects. For this this is one particular permutation. This represents one document. There are going to be another R factorial times N minus R. There are going to be a total, sorry, R factorial times N minus R factorial documents that represent the same individuals being selected, right? Because they stay on the red tray means I can rearrange them. Once they are on the red tray, they are indistinguishable. They're all selected. I can erase 1, 2, 3. R, I can say selected, 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 and here not selected, not selected. You understand? So now it becomes like a word which has R letters identical and another N minus R letters identical, only 2 different letters. Good. If you don't understand, guys, we will talk about it, right? It's this type of thinking, you need to develop your facility with it. So in general, right, this is the document that I would have selected for problem part 1, right? So I would have printed the document now that I already have combinatorics as a tool. And the document has women listed by index, in other words, listed from smallest selected to highest selected. Men also listed from smallest selected to highest selected. That's why those bars don't have bars that separate them. So this is one box. I can count this experiment, right? How many ways to select women? This corresponds to 5, choose 2. Right? So for example, if the women that were chosen are labeled 2 and 5, I have to put 2 first and 5 second. Okay. If the men that were selected were 5, 1, and 7, 4, 1, and 7, I have to put 1, 4, 7. I have to put it in order. Okay. Because once I select them, I can fix an order by which I hold them to be, right? So this box, I know how to count separately. This is 5, choose 2. And this box is 7 choose 3. Okay, and then between them, since those are two experiments, I use the principle of counting. I multiply. So the answer is 5 choose 2 multiplied by 7 choose 3. You understand? So I already developed a counting procedure for a subset, so I know how many ways to fill in this form, and I know how many ways to fill in this form. And now this is two experiments, separate experiments. One does not affect the other. But the way you fill this part does not affect the way you will fill this part at all. So that's why you multiply. Okay? You understand what I mean, right? So it's 5 choose 2, 7 choose 3. Now, what about the second possibility? Two of the men refuse to be together on the committee. What can you do now?
Seven choose one multiplied by 7 choose 1.
You have to be careful, guys. You see, Valeria, very, very careful. You see, documents, right? You're a bureaucrat now, right? So everything that you do, you have to have papers for it. Okay, so always, until you can do the papers mentally once you're trained, but do them actually, right? Imagine the document and fill it out. Because if you cannot imagine the document, very likely you make mistakes. And those are, again, very easy questions. They will be harder. Okay, I need you to think of a document.
Professor,
Yes, go ahead.
I was thinking, I wasn't sure that you like divide by 2 factorial again, because it's either like those two, if there's two people not, right? There's either there's two together or there's like, you know, they're separate, but there's only like, oh, I mean, a number of possibilities where there's two of the
Yes.
three are refuting people.
So guys, my plea to you, right? Never think about multiply or divide or add. You see, those things are secondary. Think about why is it that you're doing something. It has to be crystal clear. What's the document, why you feel it this way, and why is it multiplication or addition or whatnot, right? It has to be very, very precise thinking that you need to develop for this class. Because you see, you say 2 factorial, you can kind of go and torture yourself and find what's the mistake, but the mistake is ambiguity. All right, you need to know how the document is constructed. Okay, and if you want to, okay, I'll wait a little bit, and then we can talk about it together, right?
So, Professor,
Yes.
so because these two men, it's basically saying that we can't have them in the same category at the same time.
They cannot be selected together, right?
So could we create another category just for them, just so to make sure that they're not together? So like as a bureaucrat, you have the two women that selected, the 3 women that are not, that's listed in the documents. And then for the 2 men that don't like each other, we have a document where it lists one of them being selected, the other one
yes,
not.
you can create documents for them, right? Or you can do anything. There are many ways to count. As long as you have a document and you understand how to interpret it, you will be able to count it.
And then we'll have 2 more men that selected into the committee, and then 3 more that are not. So we'll have 3 types of documents. So for the women and the 2 men, and then the other 5 men that are present.
We can do that. I'll show you several ways, right? So once you're ready, guys, I'll let you think only a little bit, as we need to move.
I have a question.
Go ahead, ask.
So when you're talking about like a third document with like the 2 men, but aren't there situations where neither of them are selected?
Yes. First of all, I was not talking about, I'll show you my documents below. Hopefully they will be clear, right? But you see, there are many ways. Some of the things that we're going to do, it's called combinatorial proofs. And those are just comparisons of 2 documents that count correctly the same phenomena, but do it differently, use different strategies. Then you can have interesting identities, you understand? So there is not necessarily one way to do it. There may be infinitely many ways to do it, right? As long as you can find one that counts it, you are able to deal with a particular situation. Ready, Shabeli? Nice. By the way, yes, either your rabbit or your face once you have to show, right?
Say that again. Sorry.
Either rabbit or yourself.
Right now.
No. If you're embarrassed or you cannot, no, you don't have to right now, right? But eventually, I hope at least once. I need to see what people are like.
Right. Sorry.
I hear in your voice you're nervous, and I don't want to make you nervous. So don't worry. Right? No pressure. No pressure whatsoever.
Camera right now.
Okay. No pressure whatsoever. Okay? I know the situation. All right, one person is ready. Guys, there are also problems, homework problems. I'm not collecting them, but you should practice as much as you can, right? There are suggested practice problems. There are also the textbook, right? You can open the textbook. There are some problems that are solved. You've all been able to find it, yes? The textbook on the website. Okay. So in the interest of time, let's move, guys. Let me show you how that, what's my document, okay? So you see, it's the same document, but now I'm going to exclude certain situations, you see? This is what I imagine. I imagine you have women and men, right? We have the previous document and we have this situation. We are going to search for documents that contain men 1 and 2. I label them as 1 and 2. They are the enemies, okay? So if I see a document of this form, I'm not searching in here. I search 1, 2. So I'm making a search for the M category. Once I find M2, I throw the document away. You understand? So I'm throwing all documents where no matter what's written here, as long as I see 1, 2, and something else, I'm throwing the document away because that's an impossible committee. What is throwing away? What does it mean? So in general, we used to have 5 choose 2 times 7 choose 3 documents, right? Those are all the documents. Throwing away means what mathematical operation? So when I throw away, I have fewer documents. What mathematical operation is that?
Subtraction.
Subtraction, precisely. So I will take this number and I will subtract from it how many documents are in here, right? Now I need to figure out, because I don't want to do it one by one, I need to figure out how many documents I will subtract. How many ways are there to fill in this form? Well, for the women, we have still 5 choose 2 ways to fill in the form. But this form, look at it, 1, 2 is already there. So the 2 men were already removed. Out of 7 minus 2 men, I need to only put in 1. Understand? So filling this document, 1, 2 is already there. I don't have access to those numbers, so I have numbers going through 3 all the way to 7. Altogether, I have 7 minus 2 numbers. I need to pick one number. Right? 7 minus 2 is 5, and I choose 1. Right? 5 choose 1 is 5. So it's 5 choose 2 times 5 that I have here. Okay? And so the total number of documents minus this many documents that I throw out is the desired number of committees. You understand how I did it? There is another way to do it naturally, right? I will show you in a moment another way of doing the same calculation, right? Alternatively, I can do the following, right? So I can imagine the document, I'm just counting only how many ways to put in men, right? So one possibility is that I have neither of the enemies, which means 7 minus 2. I have 7 minus 2 options, and from them I need to choose 3 because I need 3 men on the committee. 7 minus 2 because the 2 people are excluded, they're already taken care of. So 7 minus 2 choose 3, both enemies absent. That's how many possibilities of just filling in this box without having 1 and 2. Okay, plus 7 minus 2 choose 2. Now why choose 2 and why 7 minus 2? So I eliminate 1 and 2. I put in 1 as the input. I put 1, but 2 cannot be put as an input. So 1 but 2 is impossible. So it's 7 minus 2. I need additional 2 elements. You understand? I don't have access to. I've already put in 1 as in. I have another 2 places, and I don't have access to either 1 or 2. So it's 7 minus 2. Choose 2. Enemy 1 is present, but enemy 2 is absent. Similarly, I can put in 2, and I don't have access to 1 or 2. and I need another 2 places. So it's 7. So it's 7 minus 3, choose 3, plus 7 minus 2, choose 2, plus 7 minus 2, choose 2, or altogether this is 5, choose 3, plus this is the same number twice times 5, choose 2. Okay, this is how many ways to fill in only this box for men without having the number 1, 2. Yes, I was hearing the word.
I have a quick question. So are you using addition here because these three conditions can't happen at the same time?
Precisely, exactly.
Okay.
I'm using addition because when I use multiplication, that's just a quick way of doing addition, right? Exactly, they cannot happen at the same time. So I just imagine for a moment, I don't see the W here. I just imagine how many ways to fill in this box under the condition that 1 and 2 cannot be together, right? So one way is I see neither 1 nor 2. Right? This is the situation I fill in without. So I imagine this box, this document where I'm not allowed one category, not allowed to put 1 and 2. So that's one type of document. That's something like Shotaro, I think you suggested it, right? I cannot put either 1 or 2, and I need 3 numbers. Another possibility is that I have to put the number 1. I cannot put 2, so I already have the number 1. I have 2 degrees of freedom. I have 2 people that I need to select, and I cannot put 2 there, right? So I have 7 minus 2 possibilities for my numbers that I could put in. 1 is there, and 2 cannot be there. And this is symmetric. I have 2 there, 1 is not allowed to be there, and I have 2 degrees of freedom. So that's why it's addition, right? So this is actually 3 types of documents. One document has neither 1 or 2. This document has 1 but not 2. This document has 2 but not 1. Okay, and I can count that they obviously have the same count. So that's why it's 2 times 5, choose 2. So we have this is the number for men. Now, independently of that, this box can be filled in with 5 choose 2 ways, right? 5 choose 2 ways to fill in this box. So altogether, I have 5 choose 2 times, this is the first way to do this process, and this is the second way. So it's 5 choose 2 for women, and this is using subtraction, and this is using addition. You see, and those quantities obviously are equal because they are just 2 procedures that count the same thing, the same situation. And it's obvious that the counting, I hope it's obvious that the counting is correct. Okay, let's try another question. So we have 10 women and 16 men. And in this case, guys, it's a play on this. So we have, so we need to select out of 10 women, we need to select 7, and out of 16, we need to select 9 men. 5 men are friends and they are always together. So either they are all together or none of them is. And 2 women are enemies in this case. Okay, so those are the 2 conditions. 2 women don't like each other and 5 men will not be separated. How many possibilities to form committees now? Great, I'm glad you are, guys. We'll do it in a moment. And any questions, guys, we can talk after class, right? We don't have to finish at this particular moment. All right, guys, let's try to see the problem through. It's now very similarly, right? We have the same form, women and men. So the women are labeled 1 through 10, and 1 and 2 are enemies. The men are labeled 1 through 16, where 1 and 5 are friends. Okay, so here is, I think, the simplest way to, we need to know how many ways are there to fill in just for women, right? So for women, I can, I have, without any restriction, 10 choose 7 possibilities, 10 choose 7 codes, but some of those codes I need to remove. How many codes do I need to remove? Well, the codes that contain both 1 and 2, it's easier to do subtraction here. Codes that contain 1 and 2, they are exactly 10 minus 2 codes, choose 7 minus 2 that contain 1 and 2. Do you see that? Why 7 minus 2? Because if the numbers 1 and 2 are already, no trouble, Mauritia. So 7 minus 2 means what? Means 1 and 2 are already there, and there are another 2 places, so another 7 minus 2 places for the remainder. And 10 minus 2 means I don't have access anymore to individuals 1 and 2, right? So it's the form that begins with 1 and 2 followed by everything else. So we have 10 minus 2, choose 7 minus 2 possibilities to fill it in. We need to subtract. Now, what about the friends, right? The friends, for the male category, I either have them in, so I either have them without, so then they're not part of the committee. So it's 16 minus 5, I have no access to them, and I need the full committee, so I need 9 members. Or I don't have access to them, but they're already placed in my form. So there are 5 placed in my form, and I need additional 9 minus 5 vacant places. So it's this plus that number. You see, this is the possibility of filling the box for men. So then the answer is simply by basic principle of counting. If I know how many outcomes are in this box, and I know how many outcomes are in this box, I just multiply the number of outcomes. Okay, that's what the idea is. I know how many outcomes for this experiment, how many outcomes in this experiment. By the way, this means that I write the numbers in ascending order. So, right, first number, smallest number is first, next smallest next, and so on. So the answer is 10 choose 7 minus 8 choose 5. That's for the women, multiplied by 11 choose 4 plus 11 choose 9. That's for the men. And there is one more problem. It's a bit more complicated. Maybe I will not answer it during this class, since you might want to think about it. So there are n antennas. You see, n antennas and objects that look exactly the same, antennas, or if you want to, batteries, right? So they are n antennas, of which m are defective and n minus m are functional. You cannot tell the functional antennas apart from each other, and the defective ones you cannot tell apart from each other. How many linear arrangements are there in which no 2 defectives are consecutive? Understand? So it cannot have, you cannot have 2 defective antennas consecutive. Do you understand what I'm asking? So it's like a pattern. In a simpler language, this is what I'm asking. Imagine you have white pawns and black pawns. Altogether, you have n pawns. M of those pawns are black, and n minus m are white. How many arrangements are there where the white pawns are not grouped more than one at a time, right? So you don't see a string of 2 white pawns. That's essentially what this problem is asking. You see, so you cannot see a pattern of the form white, white, right? So you can see a bunch of blacks, black, black, black together, but you cannot see white, white together. That's pretty much what this problem is asking. So that's a difficult question, perhaps. All right, so that is what we covered for today. If you would like, stay for office hours. I will turn off the recording, and we can talk about whatever you'd like to talk about, whatever was interesting to you.